Hey guys, it's Simon and welcome back to the last part of this RPG Kotlin LibGDX tutorial series where we are going to implement the AI for our slime. So our game, or at least our, how did I call it, the recipes of different solutions to different problems of game development is almost done, because we now can, for example, move around our character. We have there this AI state machine that our player is always correctly just in one specific state, that he cannot move from any state to any other. So there's certain logic in it that, for example, he cannot move while attacking or things like that. We have that damage system that we can attack and kill at the moment these slimes. We have the collision part in it. We can also open and interact with other entities, like for example this chest to open it up. We have music and sound available. So everything is looking great. The only thing that we are missing is now this AI for the slimes. And there we are going to introduce so-called behavior trees, which is the second part that comes with the LibGDXAI library. And before we dig into that, I want to mention here that this is the topic where I have the least experience with it. The first time I learned it during the Quilly Crawler game that I developed, and someone on my stream, so on Twitch, he helped me understanding that, because what I personally think is that the documentation behind the theory of behavior trees and how to use them and so on, that one is really well documented and great, but it lacks a lot of examples for coding. So how would you then implement certain features with the library there? In my opinion, it is pretty bad, and you really have to look around yourself. And what I did, I checked out the different test cases that they have in their code base. So there's always some tests where they, of course, test what they are implementing. And there I looked up certain things, how you could do it. And also there were some examples that I found in Google. And I think someone on Discord, if I remember correctly, from the LibGDX community, he also helped me there a little bit to find the bits and pieces that I needed to make the slime AI work. So here, please bear with me. I'm not an expert here. I also don't know what is the best way how to use it. I will just show you now my way, how I used it and how I implemented the slime AI. And I hope that helps you, and that you can then also use this functionality and maybe further improve it and adjust it according to your needs. Okay, so first of all, let's go to the official documentation, because why are we using behavior trees? So this is the official AI wiki page of LibGDX. We already learned something about the state machines. We saw how we can create the state with this enum class. And also, if you would think that further, you can already imagine that state machines, they are great, I would say, for small AIs where you don't have a lot of complexity and if you don't have a lot of states. But imagine a huge game, I don't know, an MMORPG where you have a lot of different AIs and behaviors. You could already imagine that state machines might not be the best solution out there, that it gets rather complex. And the solution that smart people out there came up with are the so-called behavior trees, which are trying to help to solve that problem. And there are two core concepts, at least in the LibGDX library, that we need to understand. So first of all, a behavior tree, as the name suggests, is a tree structure. And how can you imagine that? Let me quickly find a graphic. Okay, so in case you have never worked with a tree structure or never heard of it or know how you can visualize that. So this is basically what we are talking about when we talk about a tree in computer science, I would say. There's always usually, or I think that's actually true, there's always just one root node. So those little bubbles here, those are the different nodes, let's say, of the tree. There's always one root tree, and then depending on the implementation of the tree, so how many childs can it have? Can it only have at most two, maybe just one? Yeah, would not really make sense, then it would be more like a list. Or could it have more than two childs? So there are different implementations of trees, but it's basically like this. So you have then the child node. So from the root tree 1, the child node here would be 2 and 3, and then you go further down the tree, and at the bottom, so the last nodes are usually called then so-called leaves. So if a node does not have any other childs, like here, for example, the node 8 does not have any more childs below that, then this is a so-called leaf node usually in computer science. And the same applies to the behavior tree. So when we go back, one of these core concepts is a so-called leaf task. And those are the tasks which are at the bottom of the tree, and there you can distinguish between two things. So one task could be a condition, like for example, for the AI, are there enemy or are there entities nearby me which are hurt? And I have, for example, some healing abilities. then I could potentially heal them. So the condition would be, do I have healing abilities? That would be condition 1. And condition 2 would be, are there entities nearby which are hurt, for example. So those would be condition leave tasks. And the other sort of leave tasks would be actions, so where you then really do something. Like, for example, go to that entity which is hurt and heal it. Or if there is an enemy nearby and I want to attack it, then attack it. So the action that the entity is executing, this is really this action type of a leave task. And that is described here a little bit. So here those are these actions and conditions which are a part of a leave task. And here, for example, there would be an AI or a node which is avoid combat. The condition would be, is an enemy visible? And if this condition is true, then the behavior tree would jump to the next task if it's set up like that. And then the action would be to run away. So this is one of the one of the core concepts of the behavior tree, the leave task. So conditions and actions. And the second thing is that you normally wanted to combine those conditions and actions to build up then your complex AI. And the second core concept here are those so-called composite tasks. And there you can then simply define, when you have multiple childs below, then the node above of the tree would be the composite task, and that one defines how the different childs are executed. So it could be, for example, like here, it describes here a selector. A selector simply executes all the different childs that it has in order as long as nothing succeeds. So for example, if take cover cannot be done because maybe there is no cover nearby, then it goes to the next one, which would be leave area. If that would be possible, then it even does not go to the find backup one. So it really just selects one of these tasks, and it simply selects the first one which succeeds in that order. Another one would be, for example, a random selector, which we are not using. Then it's simply random selecting. For example, in that case, if something should sit down or if something should lie down, that would be random. And one that we will use is a sequence. So that is very similar to a selector. The difference here is that a sequence simply runs as long as nothing fails. So for example, choose cover point. We found that, so it will go to the next one and execute that in sequence. So it will then move to the cover point, and when it's there, then it will roll behind the cover point. So it will execute everything in sequence unless something fails. So for example, if choose cover point is not possible, then it simply stops. So that's the difference to the selector. Again, selector runs as long as nothing succeeds, and sequence runs as long as nothing fails. And those two things, so a selector and sequence, that is something that we are going to use for our slime when we implement that. And also one thing that is important for you to know is a so-called guard, which is, I think, documented a little bit below. Let me quickly find that paragraph. Okay, so it's already here. So it's similar like in programming. So you might know that or might already heard it. When you have at the beginning of the function, you have some conditions. And if those conditions are not met, then you immediately return the function. So those are normally called, I think, are they called function guards or method guards? I'm not sure. But the method at the beginning is guarding itself from wrong or invalid input, let's say. And it's the same here with the guards in the behavior tree. So there you could have something like, you have, for example, the attack task or the attack action where you want to attack, and that one is guarded by several conditions. So for example, can the entity even attack? Are there enemies nearby? And only if those things are true, then we can attack. So those would be those guards which we will also use and which will make more sense when we then start to implement that AI. Also, we are going to use one, in my opinion, very comfortable feature of LibGDxAI here, which is that we are describing our tree in a file format. So it will be a .tree file, which is just a normal text file. And there in that we write down how our AI looks. And there we are going to learn a couple of things regarding so how to add there an action, a condition, a selector, the tree, a subtree. So all of that will be covered, and it's also a little bit described somewhere here, if I remember correctly, in that documentation, but I won't show you that. Here it is. So this is the text format. So I won't go through that because I think it makes more sense when we just have that a real life example. At least for me, it was a little bit hard to understand what they described there, because if I remember correctly, there was also no example here, so no coding example how all of that would look like and how you load it. So I think it's easier for you to understand when we simply implement that. So coming back to our code, what we will do is now that we will implement the tree first. So we write down the file first, And then, so that you know what we are going to develop, we start with a simple tree. So for our slime, we will start at the moment that he can either wander around its original location, and the other part would be that he is simply idling around. So he is holding his position for a couple of seconds, and that would be it. So the attacking and also the moving part, that it moves towards the player and so on, that one we will implement a little bit later. We start out simple, I think, to understand then the core concepts and see how all of that works together. So in our assets folder, the way I solved that is that I created there a new folder in the assets folder, which I called AI, and then, for example, called it the slime.tree for our slime behavior tree. And how does this file format now look? So at the top, we would have normally some imports. So for example, the actions and the conditions that we are going to implement for our game, and which contains the logic for our AI. So here at the top, you would have the different import statements. So for now, we skip that. We leave that out for later on when we are going to implement that. But that would be the first part of the file. So the import, like in a normal Java file or Kotlin file, the imports at the top. So something similar would happen here in the tree file. And then you would define your tree. And the tree always starts with a root. Then below that, you can choose the composite task. So for example, if you want to have a sequence or a selector or whatever. So in our case, we want to have a selector, and we just want to pick the first action, let's say, which can be done by our AI. And one of that would be, for example, that our slime simply idles around. So we would write here something like idle. And where would that idle come from? So let's use the import now, then it makes more sense. I wanted to postpone that a little bit, but I think it makes more sense when you see that here. So we will import this idle thing. So that would be our action for the slime. So at the top, you just write import idle, and then from where do you going to import that? So this is the format for it in that specific text format that LibGdxAI accepts here. And for us, it would be the package name. So for example, GitHub, Quillraven, Mystic Woods, YouTube, I think we called it. And then in our AI package, we will maybe have something like, I don't know, slime idle or something like that. We will name it then accordingly, but this is how that would look like. So this is now an import. So the name of that import is idle. That's why we can use it here below. And where is that action coming from, or condition? It's from that specific class then in the end that we are going to implement later on. Okay, and another thing that our slime should do would be, for example, wander, which is then also simply an import here that we call then wander. And that would be, for example, slime WanderTask, so something like that. And with that, it would be a little bit boring because actually idle most likely always succeeds. So we would never reach the wander part here. And we also want to add in some random stuff, and that one we can do. So now we are going to add a certain guard to that specific task here, to the idle task, and a guard is always defined in brackets, and there is some out-of-the-box stuff available in this AI part, so LibGDxAI part here. So here we can write, for example, that we want to have a random success. So when will that guard be successful? And the percentage for that would be, for example, 0.25. So with a 0.25 percentage, so 25 percentage, we will go into this idle task. Otherwise, so if that one is not succeeding, then we will go into the wander part. There's also other things available out of the box. So not only success, I think there's also fail, which just returns then fail. And I think something else, I cannot remember it, but you can read that up in the documentation. But just that you know it, so success is something that comes in LibGDxAI, and that is simply a leave task, which always returns success. We did not come to that, but I mentioned it a little bit. So a task always returns a status, which can be, for example, success, or fail, or running as long as it's executing, or cancelled if it gets cancelled, or at the beginning if it has not started yet, then it has this status fresh. We will see that later on as well. But this is how this composite tasks are then working, and this is what I mentioned with as long as a task is succeeding or as long as a task is failing, a task is always returning a status, and depending on that status, the logic knows if it succeeded or failed. So this is something important to know. Okay, so I would say let's start with that little tree. I think this is already good enough, and then we add a little bit more features to that. So the first thing that we are going to implement, what do you think would that be? You are absolutely right. Of course, we need a new component for our component system. So I called that one AI component, but we could also call it behavior tree component or whatever, or tree component, whatever you want to have there. But I stick to the name that I used on the GitHub project. Also here something to know. On the GitHub project, I implemented actually 2 types of AI entities. So I think we implemented that in this tutorial, yeah, exactly here. So in the AI package, we have this AI entity, and on the GitHub project I have 2 implementations. I have a state entity which I use for the state machine part, and I have an AI entity which I use now for this behavior tree part. But in the end I found out that actually a lot of these things that I already needed for the states entity, I also needed that for the AI entity. So that's why I think it's better to simply combine them and just have one single AI entity which contains everything that you might need in your AI part of the game. So we will stick to that one and simply extend it. So this is just that you know it, that's a little bit of a difference between the code that we are developing and the code that is on GitHub. Okay, so what does an entity need if it is controlled by an AI? So what it definitely needs is it needs a list of nearby entities, which I think is always good for an AI, that it knows what are the surroundings of it. So what kind of entities are nearby, so that it can then react on that. So for example, if it's an enemy, attack it, or if it is an allied unit, then maybe heal it or buff it with certain things. So that's why a list of that environment, I think, is never bad to have that available. And for that, we are also going back a little bit to our box2d stuff and to the physics system, that we have a little bit of practice there as well, to update that list of nearby entities that you have here, an example as well. And the other part that we need for our component is the file path to our tree that specific entity should have. And that is simply a string that we are going to set. So in our case, that would be AI slime.tree, for example, to load that. And then what we are going to have is a late init variable, because we are going to load then the behavior tree out of that file with LibGDXAI functionality. And one of these things is a so-called behavior tree that we are going to load in a moment. And similar to the state at the state machine, a behavior tree is of a specific type. So here the specific type is E, and for us it's actually the AI entity. And I think, if I remember it correctly from the documentation, they actually called that one here a so-called blackboard, if I remember correctly. So that would be an object which contains all the necessary information that your AI needs. So for example, I don't know, the boundaries of your map, the nearby entities, the whatever, everything that is needed by the AI to determine certain things, what it should do, that should be part of that blackboard. So for us, it makes sense to have that as this AI entity. And as you can already imagine, since this is not initialized immediately and loaded out of a file, what will we need? Correct, a component listener. So let's implement that one as well. And for our AI entity, we also need access to the world of the entity from our entity world. So it's very similar like the component listener that we had for the state machine stuff. And now, so component removed. When this component gets removed, we actually don't need to do anything. And when an AI component gets added, then we want to load this tree. And this is done by a so-called behavior tree parser. So let's also create that. So we have a tree parser, which is a behavior tree parser of type AI entity, and I think that's it. Yeah, exactly. So now what we can do, we can now say from our component, the tree is equal to the tree parser.parse, and the file is from our component, the tree path. And in addition, so we also need to give it an instance of that AI entity type. So that one we also simply create. So the AI entity is the entity and the world. Okay, so here, let's see. Not sure. I think we need to pass in a file handle, but let's see in a moment. Maybe we just need to pass in the string. and then it already finds the file. If not, we are going to surround that with GDX files internal, that we have a file handle to it. But let's see, maybe that one is also working. One thing to mention here is this tree parser. So actually in another project of mine, so the Quilly crawler, I tried to implement pooling for behavior trees, so that I reuse the different tasks and trees all the time and do not create and dispose them all the time. And there is also something available in GdxAI, but I couldn't figure out how to use it. I also created an issue there. I wanted to ask how to use pooling correctly. Never got an answer there. Maybe the creators or the guys who are doing that, they are not available anymore and cannot answer. I don't know, but just that you know it, it's also mentioned in the documentation. Pooling would be available there as well. If I remember correctly, I think you set then here a certain strategy how this parser should work, and then you also need to dispose the tree. But again, for me, I couldn't figure out how it works. If someone out there knows how to do that, so how to use pooling correctly for behavior trees, would be interesting for me, and then please let me know in the comment section below. Okay, let's quickly go to our game screen that we don't forget to register this component listener as well. So we are going to add our AI component listener. And that's it. So now the only thing that we are missing is from our spawn configuration. There we want to add something now that you could specify if AI tree should be used or not. So let's define that here below. So for example, AI tree path, which is a string, and for normal or for most of the entities, it will be empty. And now in our entity spawn system, we can now check for that. So when we create our component, maybe here at the end, so if the config has a AI tree path and it is not blank, then we are going to add our newly created AI component to it and set the tree path, which is equal to the AI tree path of the configuration. And I forgot that that needs to be, of course, a variable because we want to change that later on. That should already be it, I think, for the loading part. So now down below here for our slime, we simply set now the AI tree path, which is AI/slime.tree. So this is the path to our slime here. And now we should already enter the code of our AI component and the component listener and actually load here the tree. So let me quickly try that out if that is already working. Okay, so it is not working because as I thought before, so the string that you pass in here, I guess that should be a string representation of a tree itself, but we actually want to load it out of a file where we implemented the tree. So that's why in our component listener, we need to wrap it around with the GDX files internal. So now it parses and loads that correctly, but of course it still will crash, which was totally okay because the task that we mentioned there. So we are going to import something like here, the slime idle and slime WanderTask that we are going to use below. And of course, so there you can see class not found, blah, 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 because we did not implement that. So that is totally fine. But at least the code, we know that. So that one is now working. So this is how you load a tree. And important part here, we really need to use the file handle and not just a string for the loading part. Okay, so next we want to update our tree. So let's implement a system for that. And similar to the state machine, you also need to call like an update to your tree, because of course every time you want to execute something for your AI, you want to know what it should do, and that's why it needs to go through the tree and find out what should be done. And yeah, this is done in an update call similar to the state machine, and we are going to implement that now for our tree. So let's create a new system. Let's call it AI system, and there we are going to iterate over all entities that have an AI component. Okay, so this is the boilerplate implementation. We have access to the AI components. We have an iterating system. And here, just to be safe, maybe let's also add here that an entity must not have a dead component, because for entities which are dead, we don't want to update their AI most likely, because we don't care about that anymore. They will be removed anyway shortly. So let's ignore them as well. And here it's now very simple. So just from our AI component, from our entity, there we simply, from our tree, not from the tree path, how did we call it? From the behavior tree, we call the step function. Okay, it's called step, not update. And this is now really executing the tree. So it starts from the root and then goes through the tree with the different composite tasks and conditions and actions, and finds out what needs to be done, and also calls then the different tasks and conditions that we are going to implement, and yeah, triggers then the different logic. So the system ready. That was quite a simple system, I would say. Now let's add that also to our game world, and there, for example, after the state system, let's add our AI system. Good, then one small adaptation, that's the last one that we are going to make for our already existing systems, is now to update these nearby entities from our AI component, so that we keep track of what kind of entities are nearby. And the way I solved that is that I reused again from Box2D the sensors. So when we go to our EntitySpawnSystem, and simply here, so where we add this AI component, so there we know that entity has an AI component. So here we also want to add now a sensor to it, so that it keeps track of what kind of entities are nearby. So we need access to our physics component. Okay, so we did not store that yet here, but let's do it up there. So this is our physics component. And now below here, we can get access to the body that we have created, and for example create a circle for it with a radius of 4 world units as an example, and that one is a sensor. And also let's give it a specific user data, and that would be, for example, our AI sensor, which we did not define yet, but let's do that here below. So our AI sensor is just a string like that, so that we can identify that and make a logic in our physics system. So this is a little recap and a little practice again with the Box2D stuff. So that is now great. Now, next thing, we need to update our physics system. And there we need to have access to our AI components as well. Okay, and now in our begin context method, where we already have some logic in here, we now want to do something like, for example, is entity A AI. That looks a little bit strange, but yeah, let's keep it like that. So is entity A AI sensor, and is entity B a collision fixture. So that's very similar like we had it before. Then from our AI components, from entity A, from the nearby entities, we want to add entity B, so something like that. So that one we did not implement yet. So how would that look? Let's copy that line from up here. So here we simply check, is entity A in our AI components, and is it a fixture? And we can also check here that the user data is equal to our AI sensor. And the same condition we want to have for is entity B. And there we want to check, is entity B in AI components, is the fixture B a sensor, and is the fixture B user data our AI sensor. Okay. Yeah, I think that should be it. Now, as always with Box2D here, we have the same thing here. So if entity B an AI sensor and entity A is a collision fixture, then from entity B we want to add entity A. And as always, we also need to remove then these nearby entities, which we do below. But again, here we have the special case that we cannot check for any specific components of fixture B or fixture A in that case, or entity B or A, because if you remember, when an entity gets removed, it does not have any of these components, so we cannot really check for that. So we really check here. We do the same thing as we did up here. So we just check, is it not a sensor? Then let's remove it. So here also make a minus out of that, so that we have the same code, let's say, as above, and now we only need to copy and paste the condition from up down there. So those two lines here. That's it, I would say. So this should be already the correct code to update the nearby entities of our AI. Okay, and now to the interesting part. I always forget to close the console, which might be a little bit distracting. Sorry for that. But yeah, so now we are coming to the interesting part. So we are really going to implement now the leave task. So the condition and the action that we are going to need. So let's quickly go back to our tree. So currently we don't really have any condition, so we don't need to bother about that. We just have two actions. We have idle and wander for now. So that is the interesting part. And what I did there, let me quickly show you something. So from LibGDxAI, they support a so-called leave task that you always need to extend, and there you need to implement a couple of methods. So there's a copy to function. So this is used, I think, when, first of all, when a tree gets created, I think also in case of pooling, when the tree gets reset and so on. So there, this copy to, so you get in the task, actually, for example, if you have an idle task, then the task that you get in here is another idle task, and you need to correctly set it because it gets now copied to another task. So this thing always needs to be implemented. And basically, so if you don't have a very special implementation of the task, it's always the same code, and we don't want to repeat that again and again. And then the other important function is the execute function. So this was from the task. So here we are back on the leave task. So there's an execute function, and this is what you really need to implement. And as mentioned there, so there you need to return a specific status, which is either the success, failed, or running status, which defines then if the task is done, that would be succeeded or failed. So either it is done with success or done with a failure, or if it needs to continue running, so then you return running, which means that the next time you would call the step function of your tree, you simply enter that task again because it was not finished before and needs to run once more. So that's why so that's why you have this running status, that you keep on running that specific task until it's done either with a success or with a failure. So this is the important part, I would say. And also one thing, they call that here, so the AI entity, you have access to that as well in your task. But unfortunately, they call that here, I think, object, if I remember correctly. Yeah, exactly, object. And this is a keyword already in Kotlin, because it's the keyword for an, how's it called? Not an enumeration, a singleton, exactly, for a singleton in Kotlin. So that's why, let me quickly show you that. So when you would access that in the code, it will always look something like this. So object with these, how do you call that? These single quotes around that, which I find a little bit, yeah, not so nice to the eye when you read that. So that's why I usually, or what I did in that specific case, I simply implemented my own leave task implementation. So like an abstract class, one for condition that we are going to implement later on, and one for an action. Good, so coming now to our AI package. So there we are going to implement now our actions that we currently have. So let's just create a new file. Let's call that actions. And there, as just mentioned, we are going to implement an abstract class for our action, which is implementing a so-called leave task for an AI entity. And here, so instead of writing then this object in a special way, as I mentioned it before, so let's just make here an extension property, which returns an AI entity, and the getter is simply the object. So then we can write entity instead of object in our code, which is a little bit nicer. And also we are going to override this copy to function, because as mentioned, it's always the same code if you don't have anything special with your task. We will have a few cases where we want to do here something special, so that you also see that as well. But basically, whenever we get here a task to this method passed, then we also simply want to return the task, and that's it. So this is how this gets implemented. And then let's implement our idle task. So there, let's create a new one. Here we have our idle task, which is an, I cannot type anymore today, which is an action. And here we need to implement now this execute function. So here comes our logic for that specific idle task. And here's something that I wanted to mention where I'm, let's not say disappointed, but I'm missing here something in this behavior tree area, which is what we had with the state machines, with the states, where we had this on enter, or what was it called? Enter, exit, updates, and I think message. So those 4 functions of the state, they made it very convenient that you can distinguish when is the state entered, so when is the first time that it gets called, when is a state left, so when are we switching to another state, and when is a state updated. And to me, it looks like this is not available in this leave task area and this behavior tree part of LibGDXAI. So just that you know it, there is actually a start function and there is also an end function. And you might think, okay, this is actually what we want. But no, that's not the case, because for whatever reason, if a task has some guards before that, so some conditions, then the start method of that task, of that action, will be called although the conditions are not met. So for example, if we have an attack task and the condition is that our entity can attack and that there are nearby entities, then the attack task itself, so the start method, gets called even though the entity might not be able to attack or there are no entities nearby. So this start thing, I don't really understand what exactly it does. Maybe it's for really for some for general initialization logic before so when the task gets created and you want to keep certain things for forever, so some initial state initialization, but it's not really a starting point, so when the task really now gets started. And I would suggest that you implement something there yourself, or you find out how that should be used here. Maybe it's available and I just don't understand it. What I am going to show you is maybe not the nicest part, that I would extract that a little bit to support that in a more in a nicer way. So the trick that I am using, just that you know that because we're going to use that a couple of times, in the execute function, I check if the status is not equal to status running. And now in here, this is like the on enter or whatever it was called for the state stuff. So this is then only called when the task gets now really executed. So when we really want to execute that certain action, and then I return the status running. So that, so simply that this is now the initialization logic, and with returning the status running, we don't enter this specific block here again. And then below comes then the real logic, so what I really want to do with that specific task. And this is working because the status is then either succeeded or fail. Let me quickly show you that. So it's either succeeded or failed if we normally stopped the task, so if we just succeeded the specific action, or if it failed, so this is just fine, then we are in that status. Or it's cancelled. I don't know how you can reach that. Maybe when you, I don't know, destroy the tree while it gets executed or something like that. Then there's also fresh, which is just immediately when a task gets created, before any method gets called, it's in the status fresh. And the other status which we would then use would be this running. And so all other tasks will execute this, or statuses will execute this initialization logic, and then we return running, which then executes the normal logic until we either fail or succeed. And this is how I implemented that. So that specific part, maybe that should be, or I would then move that most likely into the action class and make then a separate on start method and maybe on action method or things like that, to separate the initialization logic from the execution logic, so from the real logic. Okay, so for IdleTask, what do we want to do? So actually we just want to play the idle animation of our entity, and that one we want to do for a specific amount of time. It should remain idle. So how do we do that? So actually I can return that because we need now this initialization logic. So when we first enter this task now, we want to do something. So as mentioned, we access now our entity, and there we already have the animation function available from the previous part, and there we are going to play the idle animation in that specific case. And that would be it. And below there, so there after a specific amount of time has passed, there we simply want to succeed then. So it could look something like that. So here we return the status succeeded. But what we are currently missing is this time information. So how long do we want to stay in that specific state? And there is a certain functionality available. So we could either have here just some normal variables and pick a random time between something and do everything in the code. But we can also do that actually in the .tree file. And this is what I want to show you, because maybe you have the same task but with different properties, let's say, for different entities. So maybe the slime is just idle for, I don't know, a second, but maybe you have also a troll in your game which is sleeping for a very long time, and there you maybe want to pass it for 6 seconds, and you don't want to do that always in your code and check for a specific entity type and then choose the different values. So that's why you can do that directly in the .tree file. And how is that working? So first of all, let's go to our tree file, and here in idle, after that, we can now pass in certain properties. So let's call it the idle duration. And what kind of value do we want to pass in here? So this is very similar to the import statement here with this colon and the quotes. And here we want to pass in a uniform between 2 and 3.5. And that would be, for example, for us, it would be in seconds. So between 2 and 3.5 seconds, our slime would be idle. And uniform is just how it picks the number between that, let's say, between that specific range here. Okay, and how do we now pass in actually the information that we have defined in that file into our task? You might think, okay, that's pretty easy. Let's just write here duration, and that's a float, and that would be it. Would be great if it is like that, but it is not. But it's also not super complicated, I would say. So the important part here, first of all, this is a variable because I think it's changed afterwards. So after the task gets created, and whenever in the tree we enter that specific section or that specific node, then it will set this variable, I guess. And it's not a float, it's a so-called float distribution, which comes with the AI package. And initially it can be simply null because it's created later on. And this is not enough because we are using Kotlin. We also need to add some special annotation, which is the so-called JVM field. So this is necessary when it comes to Kotlin, that this field is then correctly read by the LibGDxAI logic. I don't know the details. I can only imagine it comes down in the end to reflection, what they are using. And for whatever reason, the Kotlin class that gets generated out of that, or the bytecode of the Kotlin class, is slightly different than the Java class. And that's why we need to have this annotation there to match the conditions that they have in their logic with the reflection part. And then there's another annotation, which is a so-called task attribute, so that the behavior tree logic knows this is an attribute for a specific task. And there we can say, for example, that if it is required or not. And in our case, it is required. So whenever you want to use an idle task, then you need to define duration. Okay, then what we need is a variable with our current duration. So this is the amount of time that we are going to wait. And that one we are also going to initialize here. So the current duration is then from our duration. And if it's not null, then it is the next float, because we define here a floating number. And if it is null for whatever reason, then we fall back, for example, to 1 second. Okay, then the next thing is that now from our current duration, when we are in here, we want to subtract the delta time, which we could theoretically get out of our world. So if an AI entity has access to the world, and from that world we could get out the delta time. But just that you see that as well, that you have an example there, there's also something built in GdxAI, and they call that here a timepiece, if I remember correctly. Yeah, exactly. And from that one you can get out that delta time. Here you need to know something in addition. We come to that in a moment. And now we simply check. So if the duration is smaller than 0, or maybe entity, yeah, but let's implement that later on. So current duration is smaller than 0, so we are done with that. Then we are going to return the stat you succeeded, because now we remained idle for long enough, and otherwise we return the status running. So again, a little recap. So we have an idle task in our slime tree. There we pass in a duration between, which takes in a number between 2.0 and 3.5. And the implementation for that idle task looks like this. So we have a duration argument, which is a task attribute, and also we need to specify this JVM field. And then from that float distribution, we can call the next float method to get here this number between 2 and 3.5 that we defined in the tree file. And then we simply subtract from that time here all the time the delta time until we are below or equal to 0. Then we are done idling around. And if not, we simply return running, which means the next time the step function of our tree gets called, we again simply end up here in that specific task, in that specific function. Okay, and the last thing, so whenever you have this task attributes here, then you need to overrule the copy to function actually. So this is one of the special cases. I am not 100% sure, to be honest, why that is needed, but I just saw it in all of the examples. So that's why I also do it to just don't get any side effects. But I'm not 100% sure when that is needed and why it is needed. Maybe someone knows it and finds the piece of documentation somewhere, then please let me know. And yeah, what you need to do, so the task that we get in here is an idle task. We know that for sure. And there we simply set the duration to the duration of our current task here, and then return the task again that we get passed in here. So whenever you have a task attribute, then you also need to define that in the copy to function, that the task which gets copied here also gets the same duration. So this is something important. Now this GdxAI get timepiece element. So this is a general thing for the AI part of libGDX, because if you remember it from the state machines, there was also a function in the states interface which was called on message, if I remember correctly, which took in a telegram and I think also the entity. And I mentioned that this telegram also can be sent at a later point with a specific delay. So for example, your entity gets hurt, and 2 seconds later you want to send out an event that, hey, I'm hurt, do something. But you want to do that with a delay of, for example, 2 seconds. And in that specific use case or scenario, so with the delay of the telegram, also this timepiece of GdxAI is used. And we also use that here to get out the delta time. And of course, you might now think, okay, so but how does this timepiece know what is actually the delta time between 2 frames? So what should it return here? And of course, it does not know that. Magically, we need to tell it that. And that's why we need to do a small adaptation in our game screen. And there, what we are going to do now, so we define a delta time, which is our delta that we get in here. And it's at most this 0.25 that we had before. Then we pass in the delta time to our worlds. And in addition now from our GdxAI, the timepiece, and there we call the update function and pass in here the delta time. Oh, it's not the delta, it's the dt, to be consistent here. So that's now how this timepiece knows what kind of delta time is between 2 frames. So this line here fixes all of that. And with that, our idle task should be now complete. We need to adjust the import in our tree file. So let me quickly check. Then we have AI, and then we have idle task. So this is how we called it. Then the next one will be the WanderTask. Let's also fix that here, and let's implement that one. So what we're going to do is to create a new task. So we call that WanderTask, which is again an action. We come to the conditions later on. For now, let's focus on some rather simple actions, I would say. And let's implement again the execute function. So here, what is wandering for me? So this is also coming for me personally from Warcraft 3. And there was an ability, I think, for a tornado, which was called wander. And what does that do? So when an entity has a wander task or a wander action in our case, then it simply moves randomly around its original position. So we need to remember and store the original location of our entity. And when that is done, then we can send it around in a specific area. So for example, in a range of 2 world units or whatever, we want to send it around its original spawn or creation location, that it moves there a little bit around, but it will always return back or stay within its original spawn area. So that is the important part. So for that, we of course need to remember the start location of our entity, which is a vector 2. And we also need to store a target location. So where should it go to, which is also a vector 2. Then we are going to use the trick again from above. So if the status is not equals to status running, so this is our initialization logic, because there we need to do something now. So first of all, we need the location of our entity. So here we check, so if the start location is not 0, if the start location is 0, so it has not been set yet, then we are going to initialize it with the entity location. I think we don't have that yet, but let's implement that in a moment. Why do we do that here? Because this part here, so this initialization logic, let's say, is called multiple times, because whenever the WanderTask succeeds or fails, then at a later point, if the entity enters that again, it will of course enter again this block here, because we want to, for example, get a new target location, so different location where it should move to. But the start location itself, so the original point of our entity, should not get updated that way, because it could have moved already to a different area, and if we set it all the time, then the starting point would also be that new position of the entity, and we don't want that. We want to really store the original position, so where it was at the beginning. So that's why this check here is needed. Then let's quickly implement the location. And there, I would say it's sufficient that we just return the location of the physics body. So here at the top, for example, let's implement a new property, which is the location, and returns a vector 2. And the get function of that is simply from the physics components. We don't have that yet, so let's also add that in here. So from the physics components of the entity, from the body, we want to return its position. Let's also call that here then position, to be consistent here with the naming. And let's also rename that to start position and target position. Okay, then also when we enter that, of course, we want to change the animation to the run animation. So above we set it to idle, and below here the animation should be run. Then we have the start position. We also need the target position, which is simply a random position around the start position. So here, first of all, we set it, and then the x coordinate is plus equal. To keep it simple, let's just take here, I don't know, a range between -3 world units and +3 world units. And the same for the y coordinate, so that we have a random area around that. And here also return now the status running. So again, we could pass in here that specific range via a task property or task attribute, like we did it with the IdleTask. But to keep it simple now, you saw how that works before. We will skip that for the WanderTask. We don't do that. And down below here, so let's also return here by default the status running. And here we want to check now something. So if entity, and there we need a new function where we check in range, and we pass in a specific range. Let's say half of a world unit, and how close is it to the target position? So is it in range of half of a world unit within the target position where we want to go? If yes, then we return the status succeeded. And also, because the entity is most likely currently moving, we also want to, let's call it stop movement or something like that. So this is what we will need. And up here, so there's also something missing. So of course we want to entity move to, and there we pass in the target position. So those are the pieces, bits and pieces that we are currently missing. We need a function where we can say our entity, okay, move to a specific position. Then we need a check. So is the entity within range of a specific position? So here it's again just hard-coded half of a world unit. Again, we could pass that in as an argument to the task. And then we also want to stop the movement of our entity. So let's implement those 3 things here. Good, so this is the skeleton, let's say, of those 3 functions that we are going to implement. And let's start with the easier one, which would be the stop movement. So stopping our movement, as we know it from our move system, is simply setting the cosine and sine value to 0. So with the move components of our entity, we simply set the cosine to 0 and the sine value to 0. So that will stop the movement of an entity, and that is all that this function is doing. Then the next one is, let's pick this move to area. So that's also quite simple, I would say. We need a little bit of two-dimensional math here, but nothing too crazy, because we know the position of our entity and we know the target position. So we have 2 points available, and the only thing that we now need is actually the angle between those 2 points, and then we can set the cosine and sine value correctly for our move component that our entity is moving to that point. So what we need here, so as mentioned, we need first of all the target x and the target y, which we get from our target vector. Then we need the source x and the source y, which is the entity position, and there again we take it out of the physics component as an example. So we have the source x and source y, and that is from our physics component, from the body, the position. And now we want to set from the move component from our entity, we want to set the cosine and sine value, and for that we need the angle. And we can get that with the math utils from LibGDX. There is the arcus tangens, I don't know how to pronounce that in English, 2, so the arcus tangens 2, and there we need to pass in a y and an x value. And that is simply the target y minus the source y and the target x minus the source x. And that gives us back the angle in radian, if I'm not wrong. Returns the angle to the given point in radians as a float. Yeah, perfect. So in radians. So that's why the cosine can then be, again, from the math utils of LibGDX, it's the cosine, where ideally we can pass in the radian, which we already have available, and same for the sine value, but there we call the sine function, of course. And that's it. So this is this move to function. So again, we get the angle between the 2 points, and then we just set from our move component the cosine and sine value that an entity will move towards that. And the last thing now is that we want to check if the entity is in range of a target position, and we also pass in here the range to check. And what I use there is, again, something which is already available in LibGDX. So when we have a rectangle, okay, that one has a function which is called contains, and it checks if that point is inside the rectangle. And the rectangle itself is simply the position of our entity, and then we go from that position minus the range to get to the left edge, and plus the range to get to the right edge on the x coordinate, and same with the y coordinate to get the top and bottom edge of the rectangle. So we simply create that, and then we check if that specific target here is inside. So what we need is, again, the physics component from our entity. Let's get that up here. Then again, the source x and y. So this is the center of the body position here. What we also need is actually the offset to really get the correct position of our entity. Also, we need the size to really get the correct bottom left and top right position then in the end. So let's call that offset x and offset y. So offset x and offset y. This is from our physics components, the offset. And then we also have the size x and size y. Also from our physics component. And here we make a little trick. So this is a variable, and the real size is now plus equals the range, and the size y is also plus equals the range that gets passed in. And now we can create our rectangle. And because we will need that multiple times for many different entities, maybe even multiple times per frame. So let's create a temporary rectangle that we use only within that function. And let's create it, for example, here at the top. So private temporary rectangle, which is simply a rectangle from LibGDX. And now down there, we can now set that. So what is the x coordinate? So this is the source x position plus the offset. How did we call that? Offset x minus the size. And only half of it. Then almost the same we have for the y coordinate. So that's the y position plus the offset minus half of the height. And the size of this rectangle is now simply the size of the x and size on the y axis. That's it. That should spawn or span that particular rectangle that we need. And now we simply need to return contains the target position. That should be everything that we need. So those are our three functions for move to, in range, and stop movement. And coming back now to our action. So now this code should compile. And that should be it. So now, after quite some time, it should be possible now to load that simple tree here and make our slimes now move around, stay idle for some time, and wander around. Let's see. Okay, so we can see them moving around and also idling around from time to time, so they simply do nothing. And you see them crazily running around. Super cool stuff. One thing, so they are moving quite fast. What I did here, but I don't show that now in this part. I think you can figure that out yourself. Let me close that again because of the music. So two things that I want to mention. So first thing, when we go to our WanderTask, we were in the actions file, exactly. So there, what I did in here, when something is wandering around, I also slow down its movement. So there's another function which I called, I think, I don't know, slow down or whatever I called that, I cannot remember. But what that simply does is setting a flag on the move component. And when that flag is set, then an entity actually gets moved just with, I think, a quarter of its original speed, so that it does not speed around like it does right now, so that it really just slowly moves around. But I think that's quite easy and nothing that adds now something to this specific part, so we will skip it. And of course here at the end, so when we succeed, I also return the move speed to its original part. So this is one thing that we did not implement here, but just that you heard of it. Another thing, it could be that this target position here is actually inside an object that you can never enter. So for example, let's quickly start up the game again. And let's imagine that our target point would be the tree, that position here inside the tree. But because there's some collision, I cannot really get to that specific point. So it could happen that one of our slimes currently gets a target position that it can never reach. So it will move towards the tree here forever because it can never reach that specific location. What is that slime doing? Okay. That also got now a crazy position. Maybe even outside of the map could also be the case. And yeah, I think it actually got something outside of the map. So it now tries to always get to that specific location, which it cannot do. So now we have a real life example. And I thought about that. So one solution, let me turn off the music again. One solution could be that you somehow have a method available that you know if you can reach a specific point. There's also something available in Box2D. I think you can make a raycast, I think it's called like that, and you can check if you can reach a specific point or if there are collision objects available. Another solution would be that you have how's it called, pathfinding algorithm in your game available, like A star, and then you simply know, can I reach that specific point because the algorithm returns you a path or not. Those are, I would say, more complex solutions. Great if you have them available, and if you need them in your game, then just use it. Also LibGDX again supports that, so the A star algorithm would be supported by this library. But a much simpler solution, in my opinion, and the one that I would choose for that simple game, would be that you just add a time. So very simple, like we have it with the IdleTask. You just add a duration. So for example, I don't know, 5 seconds. And if the entity does not reach the target point within 5 seconds, then also just succeed this task and give up to try to reaching that specific point. So that would be also one solution, a much simpler one. So just that you heard it. Okay, great stuff. So we have now an IdleTask, we have a WanderTask. The only thing that we are missing now, I think, is the AttackTask. And I already see, so this is a long part. I knew that will be a long part. But also to motivate you a little bit, that is the final piece. Then, and actually everything that you would need to know for that attack task, you already know it. So if you want, you can try it out yourself. And if not, please follow along. And now I will show you how I implemented that specific attack task and also how I enhanced the tree. So coming back to our tree, we want to add here now to our selector also an attack stuff, and we want to add now some conditions as well, and guards for our attack task as well, that we really only attack something if an enemy is in range and if we can attack. So if something is in the attack range. And also what I added, just as an example for you that you have that as well, whenever a slime attacks, so after he has attacked, he will wait a specific time and do nothing because he needs to like regenerate from its last jumping attack, and that takes some time. So there is also something built in into LibGDXAI that we are going to use. And to keep it a little bit more structured, we could theoretically simply add here all these things that we need for the attack part of our AI. But to also show you an example there, you can also use subtrees, because for us it's a quite simple tree. We don't have a lot of different things in there, but you can imagine that that can get pretty complex depending on what kind of things you want to do in there. And to keep it a little bit more structured and also to reuse certain things, you can implement certain or so-called subtrees. And there, so here at the top of our selector, let's call that now, for example, $attack. That one is highlighting that that will be a subtree. And how do we implement a subtree? So here at the top, we just say subtree. The name of the tree is attack. And now the parser of the file knows, okay, with that sign, it will look for a subtree of that specific name, which it will find here at the top. And then just whatever we have defined in the tree up there, it will insert it here below. So that way we can keep it a little bit structured. And for our attack tree, we want to have a sequence now. So we don't want to have a selector. We really want to run through all the actions which are defined here. And the first guard that we are going to implement is an enemy nearby. That makes sense. Another thing, can we attack? So are we, for example, currently attacking or maybe stunned or whatever? So that one we are also going to implement. And if both of them are true, so if both conditions are met, then we are going to attack. And after an attack, we are going to wait. So this is now built in into LibGDX. There we don't need to implement anything. And we wait for a couple of seconds. And again, we have here a uniform between those two time frames. So this is how long our slime will wait after an attack. So what do we need? So first of all, we need another import. We will then call that an attack task. And we also have conditions. So let's make here also some comments that you see that here. So those are our actions. Those are our conditions. And there we have several conditions. So we have the IsEnemyNearby condition. That will be in capital letter. And we also have the CanAttack condition with the question mark in the end. So there you can use, I think, almost any character that you want. And in the examples, they always use this question mark, which in my opinion makes it nice to read, that you see that this is a condition. Okay, so I would say let's start with the conditions, because we did not do that yet. So let's create another file and call it conditions. And now, very similar to the actions, I also implemented here an abstract class for a condition. Let's take over that code here and let's call that condition. And the condition is really something special in my opinion, and very simple, because it either returns true or false, let's say. So the condition is either true or false, and speaking in this LibGDXAI terms, it's either status success or status failed. And we don't want to always implement this if something is true, then return success, otherwise return failure. We are going to implement that here in the abstract class and simply override the execute function. And we're going to implement a new function, which we call condition, and that one returns a Boolean. And now it's simple. So if the condition is true, then we return that you succeeded. And otherwise we return status failed. And we can lift the return out of here, and that would be it. So this is the implementation of a condition. Let's also use here when, and make it then also in a single line. I think that's even more readable than the version before. Okay, and what kind of conditions do we need? So we need IsEnemyNearby and we need CanAttack. So we have a CanAttack condition, which is the condition that we just implemented. There we need to implement the condition function, of course. And the other one is IsEnemyNearby, which is also a condition. And also here we need to implement the condition function. So here I make that again part of the AiEntity. So we simply return entity hasEnemyNearby, for example. That would be the function here. And similar here at the top, here we also just return entity CanAttack. This is also let's make it a function. So with that way, since it's returning a Boolean, that will be then simply become one-liner. And now let's implement those two methods in our AiEntity. Then we already have available the conditions that we need. Okay, let's start with the hasEnemyNearby. So what we want to have here is actually from the nearby entities of our AI components that we did not use yet so far, but we have them already available. So here we simply want to filter for all entities which have a player component and which are not dead. So those are the enemies from the perspective of a slime. And if there are any available, at most one in our case, but theoretically could be of course multiple players nearby, then this function will return true. And also to have that here available, let's make it private for the time being, a utility function which returns the nearby enemy entities. So let's call that nearby enemies, for example. And here from the AI components, which we don't have access yet, but let's also bring that in here. Okay, then also this is a function, of course. So from the AI components of our entity, there we return. Let me write that a little bit differently. So here we have the AI component, and now from this AI component, from the nearby entities, we apply a filter. And the filter is that the entity is in the player components. I think we also don't have access to that yet. And from the live components from that entity that we are going to check, it must not be dead. Okay, so let's also add the player components to our AI entity. Just like that. And now below, that should already work. But of course, we need to return here a list of entity, for example. Okay, and this function now simply should be, so nearby enemies is not empty. Then let's convert it to an expression body. We can also return that a little bit simpler. Good, so hasEnemyNearby should work. So we check, or we calculate the nearby enemies, and we check that this is not empty. Then we know that it has nearby enemies. Okay, and the next thing is CanAttack, and that one is a little bit more complicated. Not super complicated, but first of all, of course, we want to check if from our attack component, the status, let's say the attack status or state, I think we call it, is ready so that the entity can really attack. And this method also checks a second thing. So first of all, it needs to check, is there a target nearby? And if there is a target, is that target in attack range? So can, for example, when the slime is next to the player, can he really attack the player because he is close enough? Because when for example, the slime is very far away and there are actually no entities that he could attack, then of course he cannot. He can attack, but he cannot do that with any sense because it just attacks the air. And we want to check here, can he attack an enemy entity? So this is the second thing that this function is going to check. Okay, I just had a technical break there, so don't wonder about the time that has passed in here, but also your instructor sometimes needs a little break. So where were we? We were at CanAttack function. So here we want to access the attack component from our entity. And the first check, so if the attack component is not ready, so we cannot attack, then we return false. Otherwise, so here we know the entity theoretically can attack. Now we want to check, is there an enemy in attack range? So for that we can reuse already our method here below. So we get the nearby enemies, and there we get the first one, or null if it is, if there is no nearby entity actually, nearby enemy. So let's call that enemy. And if the enemy is null, then we also return false, because that means there is no enemy that can be attacked. And if there is an enemy, then we return in attack range, for example, and there we pass in the enemy entity that we have found in here. And actually we have this function already available, I would say. So this is the inRange function. We just need to pass in here the target, and that one can be simply achieved because it's actually the same as we have here at the, where do we have it? Here. So that first part here is actually what we want to have for the location check, I would say. Maybe it's not 100% accurate, maybe it needs to be fine-tuned, but for the time being I would say that's it for us. So we just need all of that information below for the enemy that we have found. So we get here the enemy physics component, which is from our enemy, the physics components, and then here simply the position, and then we pass in here the range. The range itself would be from our attack component, the extra range, I would say, which for a slime would be 0. But for a player, for example, or other entities which might have an extra range on the attack, we want to take that into consideration. And the target that we are going to check is simply a vector 2 with the source x plus offset x minus size. No, let's just keep the center actually. I think that should be already okay. Okay, so something like that. This is slightly different than the code on GitHub, but just that you have an idea. It does not need to be 100% perfect here, but just that you understand what is the theory behind that. So we simply check here, so is the attack state ready so that the slime, for example, can attack? And then we also check, is there an enemy nearby? And if yes, we check if the position or if that enemy is in attack range of our slime. So maybe just checking for that specific position is not accurate enough, because actually we always check for this hitbox, if I remember correctly, if something can be attacked or not. So maybe that should be a rectangle, but it doesn't matter. So as a showcase now, just that you have here an example. So here we just check for that the position of the enemy that we find is within this rectangle or attack range of the AI entity. And that one, okay, we can replace with the Elvis operator, it seems. Okay, also fine for me. Makes it a little bit shorter. And that should be it for our conditions. So we have the can attack and we have the hasEnemyNearby IsEnemyNearby condition. So back to our tree here. So we have implemented those two conditions. The only thing that is missing now is the attack task that we are going to implement. And for that we go back to our actions and we implement an attack task, which is another action. So here again, if status not equals to running, we need some initialization stuff. Then what do we do? First of all, we set the animation to the animation type attack. We also set the play mode to normal, And I think we reset the animation here, I cannot remember, but just to be safe, we want to play this attack animation just once, and we also want to start an attack. This is how we called it before. So this sets this attack component stat to prepare, so that our slime is then going to attack. And then if we are not there, then, so if we are not initializing, then we simply check, so from our entity, is animation done? And when the animation is finished, then we go back to our idle animation, for example. And we also stop the movement. And then we are done. So our slime can, while he is moving, he can attack. So that then makes this little jump attack animation, let's say. So if the attack animation is played while moving, which is allowed for our slime, and when he is done, he simply stops moving. And in our tree, we then said that he should wait for about a second or two after the attack, which is the time that the slime needs to recover. So let's see. So theoretically, that should already work, and our slime should now attack us. We did a mistake, obviously, somewhere. Yeah, okay, we need to rename that to attack as well. Let's see. Okay, so let's get close to our slime. Okay, something is not working, because obviously he's not attacking us. Let me debug it. What is it? I assume there is an attack range, or something is not properly working. Or maybe the nearby entities are not set up yet correctly with our PhysicSystem. Let me find that out. Okay, found it. So there are two minor things, I would say. So first of all, this in range, as I expected, it's not 100% accurate and not ideal with the way we are working here. But anyway, for that part, it doesn't matter. I think you can fine-tune that yourself or have a look at the GitHub project. What I did here now to fix it, so this extra range is 0 and the size of a slime is 0.6. So it needs to be very, very close to the player to return here true. And for now, just to make it work, I just added here 1.5 world units to that check. So if the player is within 1.5 world units, then this CanAttack function will now return true. That was the first problem, that one always returned false. Another thing, which is not related to what we implemented today, but is related to the attack system that we have, there is a function that we call, which was called start attack. And that one is only setting this attack state, because we use that for the player state, if you remember correctly. But there is a second piece to really initiate then the attacking. So also something that might need to rethink that approach, which is this flag. So for the player, we simply set that when he presses the space button, so that he wants to attack, and then this flag is set. But for our AI entities, we did not set this flag yet. And I now quickly just implemented or added a second function, which I call do and start attack. Yeah, the naming is great, I know. And that simply also sets this flag now. And in our actions, so in the attack task, we are now, instead of calling the start attack, we call this do and start attack to also set this flag. And now with those two adjustments, everything is already working. So slimes are moving around, and when we get close to that slime, okay, that one is, I think, stuck now in his move task, because he never leaves that. So now when we get close to a slime which has nothing else to do, then he will attack us. Also this attack sound is played and everything is great. So this is a small implementation of how to implement this attack task. Again, in this video, we did not implement it perfectly, and there's a lot of fine-tuning that comes then to this AI part. You can check out the GitHub code. So for example, what we did not implement yet in this idle task, what we would need to do, so either the duration is done, or we could also check if there is a nearby enemy that he could attack something. Then of course we want to move out of the idle task and go to attack task. Same for wandering, if there would be an enemy nearby. So we not only checking that we reach the target position, we would also check, is there a nearby enemy? Then we also want to stop that specific task to go to this attack stuff here. And in addition on GitHub, I also added a move task, which is simply doing when an enemy is close but not yet in attack range, then the slime is moving to that player, and once the slime is in attack range, then he is really attacking. But I think for the purpose of this video, that's not relevant. So the important part is that you have now seen how you can define such a behavior tree, how to implement conditions and actions, the different task guards that we have seen, the different composite tasks, so the difference between a selector and a sequence, and that there would be other stuff. Also the purpose of the statuses with succeed, failure, and running, and all of that. So I think that is the important part, and I hope that I could show that in a meaningful way to you, that it makes sense. And with that, that is the longest part, and I knew it from the beginning that also would be the, maybe not the most complex part, but at least a longer part, because of all the different things that we need to implement here with the AI. And as you've seen, I think it's a very cool library and very nice, and you can implement very cool and complex stuff with that. And I like the way that it is structured, that you really have then those different tasks, or the conditions and the actions, and you can combine that a little bit freely in these tree files, that there's also out of the box something available like this weight stuff, or that you succeed or fail with a specific percentage, that you can pass in those attributes out of this file. So I like that a lot, and I think you can do really amazing things with that small piece of the library. Okay, yeah, that's it for the entire tutorial that I wanted to show you. I hope you had fun. Let me know in the comments below. I saw once that in the analytics part of YouTube that over 50% are not subscribed to the channel yet. So please, if you have time and if you like the videos that I made, then also please leave a subscription here. But what I am more interested in would be comments, that you let me know what could be improved, maybe what kind of things are missing, maybe certain things that I did not understand correctly and maybe teach you the wrong way or taught you the wrong way. Let me know. Also, if you would be interested in other things as well, then I can also add that to that tutorial series, because as mentioned, it's not really a series where we're implementing a fully fledged game that you can then just roll out on any platform. This was more like different recipes to different problems, and of course there are a lot more problems and things when it comes to game development. So just let me know if you are interested in another topic, then I can simply make a video for that. In the context, I would say, of that game, it should make sense to add it there, and then I could cover that as well and just add that as an additional part to the series. So it must not be over. We can still enhance that tutorial if you want. Again, thank you for watching, guys. Have a nice rest of the week, and see you. Bye bye.